Okay, the second application of Gauss's law, we will discuss the electric field due to infinite sheet of charge. This I will assume that suppose this is a sheet of charge, okay? I will consider a small piece of a paper. Let's suppose we have this sheet of charge. Suppose this is the sheet of charge, okay? On this charge we have positive charges on the surface of this sheet. So I consider this, the sheet of charge is infinite, but I'll consider a small piece of this sheet of charge. Otherwise it is infinite, it extended to infinity. Now this sheet has a positive charges which are shown here, and if it is a positive charges, then it has some surface charge density sigma, which is equal to charge per unit area. Charge is equal to surface charge density times area. This is, let's suppose, equation 1. Now to find the electric field, let's suppose this is the sheet of charge, which is, I place it like this, okay, like in a perpendicular way. If we want to calculate the electric field somewhere here, then we draw a Gaussian surface. The Gaussian surface should be like in a cylinder. Like this is the cylinder, and this cylinder is penetrated inside this surface. It's like this. So this is the sheet, and this is the sheet. Sorry, it's not going to be straight now. Suppose this is the sheet, and we have a cylinder which is here, given here. So this cylinder is penetrated, so half part of this cylinder is on the left hand side and half part is on the right hand side. Now this cylinder has three surfaces. Now suppose this is the half part. This cylinder has three surfaces now. One surface is this, the other surface is this one. It's a cylinder, so both sides have the same area, and the third surface is this curved surface. This curved surface. Now the area of the curved surface is either this one, or it's this one, or it's this one, or it's downward. While electric field line move from here and this way, okay, or it's move from here and this way. So it means that the area of this curved surface is upward, the direction of area is upward, and electric field is in this way. So it means the angle between this electric field and this area direction on this surface is 90. So there will be no contribution to the flux from this curved surface. Now if you look at here in this part, then the direction of this area is this one, while electric field is also on this way. So it means that the angle between electric field and the area direction, this one, is 0. So we have a contribution to the total flux from this area, this surface, and also from this surface. So again we divide this cylinder into three parts. One is this surface S1, and the other one is this surface S2, and the third one is this S3. Now electric field move like this. This surface direction is this one, N, and electric field direction is this one. This is the direction of electric field. Similarly, this surface area direction is this one, and electric field also move like this. While this surface area direction is this one, the curved surface, while the electric field direction is this one. So there is an angle 90 degree. So it means that the contribution to the flux, total flux, the contribution, we can say that the flux to surface area, surface S1 is, which are represented by phi 1, and which is equal to integral of E dot dA. And I suppose this is the cylinder, okay? The cylinder is like this. It has three curved surfaces. One is this S1, and the other one is this S2, and the third surface is this curved surface, this one, S3. Now this has area A, this is also area A, because it's a cylinder, so both sides is the same area, and this area is, let's suppose this is any kind of area, its area is 2 pi r L, but we are not interested in this area because I will explain it later. Now here, if we penetrate the surface, this cylinder on this infinite sheet, then the direction of electric field from this sheet is always either this way or it's on this way, because this is the sheet. So the direction is either this way or this way. If the charges are on this side, the electric field goes on this way. If the charges, if we look at the back side, then the electric field goes from that side. So it means that on this side, the area direction is this one, while the electric field direction is also this one. Similarly, area direction is this one, and the electric field direction is also this one. But in this case, the area direction is upward, while electric field direction is this one. So the flux through surface area, surface S1 is E dot dA. So E dot dA, the angle between E and dA is sorry, I consider it to be a capital area A. So the angle between E and dA is 0, so it's E dA. But E is constant, so we have E, I will keep it outside, and we have dA. From we will get E into A. This is flux through surface S1. Similarly, flux through surface S2S, I will represent it by phi 2, which is equal to E dot dA. This integral is a surface integral, okay, remember it. So again, the angle between E and dA is 0, so we have E dA cos of 0. From this we will get E dA. Again, E is constant, so we will keep it outside of the integral, and we have dA, so E into A. This is phi 2. This is equation 1, this is equation 2, then this is equation number 3. Now flux through the surface S3. The flux through surface S3 is, which I represent by phi 3, which is equal to E dot dA. And the angle between E and dA, E is this one and the area direction is this one, is 90. E dA cos 90, because cos 90 is 0, so from this we will get phi 3 is equal to 0. Now the total flux, this phi 3, total flux phi, which is equal to the sum of 3 flux phi 1 plus phi 2 plus phi 3. Flux through surface S1, through surface S2, and through surface S3, which is equal to EA through surface S1 plus EA through surface S2 plus 0. This is the total flux. So the total flux is equal to 2EA. Also by Gauss's law, now we will use the Gauss law to calculate the total flux, to calculate the electric field. Sorry. Starting to, from Gauss law, the flux through any surface is equal to 1 over epsilon naught times total charge enclosed by the closed surface. If this is equation 4, if this is equation number 4, then this is equation number 5, then comparing equation 4 and 5, we have 2EA is equal to 1 over epsilon naught times A. 1 over epsilon naught times Q, sorry. Also from using equation 1, which is this one, Q is equal to sigma A, we have 2EA is equal to, instead of Q, I will put sigma A divided by epsilon naught. A cancel with A, so electric field will be equal to sigma divided by 2 epsilon naught. This is the magnitude of the electric field, and its direction will be E is equal to sigma divided by 2 epsilon naught into R. This represents the direction of the electric field. So this is the electric field through infinite line of charge. We already derived this formula before by using the Coulomb's law. If you memorize your, if you repeat your memory, if you check your lecture notes in the class, we derive such kind of relation by using Gauss's law, by using Coulomb's law. So this is the second application. In the next video, we will discuss some other application of Gauss's law. Thank you.